Okay, so we're going to go over the reflection that was assigned last week, where I asked for two statements, whether you agree or disagree. Right. The first statement being, if a function f is differentiable at a point A, then f is continuous. Right. So for something like this, we assume that the function is differentiable. Right. The if is the hypothesis. So we said if this is true, now what does it mean for a function to be differentiable? Right, we have a little graph here kind of showing what is happening at A, right? Differentiable means that the tangent line, the slope of the tangent line at that point, right? Or in other words, if we look at the limit definition of the derivative, when we're saying a function, excuse me, a function is differentiable, what we are also saying is that this limit exists, right? Those statements are equivalent. Right, we say the function is differentiable at A, that means that this limit exists. Okay, so let's say if the fact that it's differentiable is that if that is enough to assume continuity at the point A. All right, so what we'll do to do that, to kind of show that that is in fact true, is we'll start with the difference here, f of x minus f of a. All right, and I'm going to do a little trick that mathematicians always like to do, and that is multiplying by 1. Right, where in this case, 1 is the quantity x minus a, x minus a. Right, and again, notice that these are equivalent. This is multiplication by 1. In this case, 1 takes on the form of x minus a over x minus a. Right, now if I take the limit of this equation here as x approaches a, right, we get this here, f of x minus a, x minus a times x minus a over 1. Okay. All right, and now applying some of these limit laws on the left side of the equation, we get this. And over here, I'm going to split this up into two factors here. Okay, and now this is our derivative, right? Again, we're assuming that it's differentiable, so that limit exists, and that limit is represented by f prime of a, limit as x approaches a of x minus a, and over here we have the same thing, right? I can't do any simplifying there. Oops, limit of f of x. All right, and now this limit is, I can just plug in the value of a over here, right? Since it's just x minus a, I'm not dividing by 0. And whenever I'm not dividing by 0 or something undefined happens, I can feel free to just plug in that value. So this just becomes f prime of a times 0, or in other words, 0. And we get, just bring this down here, the limit as x approaches a of f of x minus the limit as x approaches a of f of a is equal to 0, or in other words, the limit of f of a. Okay. All right, and since this function is defined around the values near a neighborhood around a, then this is enough to show that this is in fact continuous at a. All right. So now what about for the converse of this statement, right? So the converse, we kind of flip the conclusion and the hypothesis, right? What if I assume that a function is continuous? Is that enough to show me that it is in fact differentiable? All right, and I think for a lot of you guys did have disagree, and this is true, right? This is not something that we are guaranteed to happen. All right, and I think one or two of you brought up the example, or at least referenced this idea of a sharp corner. And you brought up the function, the absolute value of x. Okay, and we said this is not true because this is continuous, but we are told that we can't differentiate at a sharp corner. And that is true, right? This is a false statement, right? And we can show that if we think of, all right, well, let's let a equal to 0, right? So what would the limit, or the limit as x approaches 0, right, of x, excuse me, the limit as x approaches 0, f minus f of 0. All right, and then here, simplifying here, we get the limit as x approaches 0, absolute value of x over x. Okay, now how do we simplify this? Well, we can see looking at our graph, right, or using the piecewise definition of the absolute value, which is negative x if x is less than 0, or simply x if x is greater than or equal to 0. All right, that's how we interpret the absolute value as a piecewise function. Now, applying that here, we look at the left-sided limit. Right, that says that I should replace absolute value of x with negative x, and that gives me a value of negative 1. Okay. And then the limit as x approaches 0 on the right side, right, or the positive side, that simply means I can just drop the absolute value and replace it with x. Okay, so we see here that these do not match, so the limit does not exist, and therefore it is not differentiable. It is continuous, but it is not differentiable, right? And again, here, I think some of your solutions did reference the fact that certain conditions would have to be met for it to be differentiable, right, and continuous, right? And here, what we just want to gather from this statement here is that continuity does not guarantee us differentiability. All right, it might be, right, if certain conditions are met, right, but we are not guaranteed that, right? But the converse, if I know it's differentiable, that definitely guarantees me continuity. Okay, so kind of subtle there what each one of these statements is telling us. Thank you.